In this lecture, I am going to explain graphical method to solve linear programming problem involving two variables only. Consider this example. A firm plans to purchase at least 200 quintals of scrap containing high quality metal X and low quality metal Y. That means the scrap should contain two types of metals, metal X, that is high quality metal X, and low quality metal Y. It is decided that the scrap to be purchased must contain at least 100 quintals of metal X and not more than 35 quintals of metal Y. That means the purchased scrap should contain at least 100 quintals of metal X and not more than 35 quintals of metal Y. The firm can purchase the scrap from two suppliers A and B in unlimited quantities. The percentage of X and Y metals in terms of weight in the scrap supplied by A and B is given below. The price of A's scrap is 200 rupees per quintal and that of B is 400 rupees per quintal. The firm wants to determine the quantities that it should buy from two suppliers so that the total cost is minimized. So this table gives the percentage of available of metals X and Y in 1 quintal supplied by supplier A and supplier B. For example, supplier A, for supplier A, 1 quintal of supplier A contains 25% of metal X, that is 1/4 of metal X, and 10%, that is 1/10 of metal Y. Similarly for supplier B. Okay. So to solve this problem, first convert to mathematical model, that is linear programming problem. First identify the decision variables. So what we have to find in this problem? We have to find in this problem the quantities that it should buy from the two suppliers, that is the number of quintals of scrap bought from two suppliers. These are the decision variables. So let x1 be the number of quintals of scrap to buy from A, x2 be the number of quintals of scrap to buy from B. So these are the decision variables. Next we have to identify the objective function. So objective function gives the aim of the problem. So what is the aim of the problem? The total cost is minimized. So what is the total cost? First, so observe the problem. The price of A's scrap is 200 rupees per quintal and that of B is 400 rupees per quintal. Okay, so 1 quintal of scrap from A is 200 rupees cost. So we have to purchase x1 number of quintals from A. So the cost of scrap from A is 200 x1 rupees. Okay. Similarly from B, 1 quintal cost is 400 rupees. So x2 number of quintals cost is 400 x2 rupees cost. Okay. So the cost of x1 quintals of scrap from A is 200 rupees, 200 x1 rupees. The cost of x2 quintals of scrap from B is 400 x2 rupees. So total cost is sum of these two, 200 x1 plus 400 x2. Since this is cost, in general we try to minimize the cost. Okay, so the objective function is minimum z equal 200 x1 plus 400 x2. So this is the objective function. Next we have to find constraints. So what are the conditions to satisfy? Okay, right, observe the problem. The firm has to purchase at least 200 quintals of scrap. Okay, so from decision variables, how many quintals the firm purchase? x1 quintals from A, x2 quintals from B. So total quintals, total quantity x1 plus x2. So this is the total quantity purchased based on the decision variables. But the firm has to purchase at least 200 quintals. Okay, so based on the decision variables, this is the total quantity. The target of the firm is at least 200 quintals. So what is the relation between these two? So at least means not less than 200. So that means more than or equal to 200. So the relation between these two is x1 plus x2 greater than or equal to 200. So this is the first constraint. Okay, next, what is the next second constraint? So observe this, it is decided that the scrap to be purchased must contain at least 100 quintals of metal X and not more than 35 quintals of metal Y. Okay, so the scrap should contain at least 100 quintals of metal X. That means not less than 100 quintals. Okay, so based on the decision variables, how much amount of metal X available in the scrap. Okay, so observe the table. 1 quintal of scrap from A contain 25%, that is 1 by 4th of metal X. So x1 quintals from A contains 1 by 4 into x1 quantity of metal X. Okay, so this is available quantity of metal X from supplier A. Similarly, from supplier B, 1 quintal of scrap from supplier B contains 75% of metal X. Okay, so 75% means 75 by 100, that is 3/4 of metal X. So x2 number of quintals from B contains 3 by 4 x2 quintals. Okay, so the scrap must contain at least 100 quintals of metal X. So 1 quintal of scrap from A contain 25%, that is 1 by 4th metal X. So x1 quintals of scrap from A contain 1 by 4 x1 quintals of metal X. Similarly, 1 quintal of scrap from B contains 75%, that is 3 by 4th metal X. 75% means 75 by 100. So x2 quintals of scrap from B contain 3 by 2 x2 quintals of metal X. So total quantity of metal X in the scrap is sum of these two, 1 by 4 x1 plus 3 by 4 x2. But the scrap must contain at least 100 quintals of metal X. Okay, so what is the relation between these two? 100 and this. At least means not less than 100, that means more than or equal 100. Okay, so the relation between these two amounts is 1 by 4 x1 plus 3 by 4 x2 greater than or equal 100. So simplify this, multiply by 4 on both sides. We get x1 plus 3x2 equal 400. This is second constraint corresponding to metal X. Similarly, for metal Y, the scrap must contain not more than 35 quintals of metal Y. So not more than 35 means at most 35. That is less than or equal to 35. Okay. So from the table, 1 quintal of scrap from A contain 10%, that is 10 by 100, that is 1 by 10 metal Y. So x1 quintals from A contain 1 by 10 x1 quintals of metal Y. Similarly, 1 quintal from B contain 20%, means 20 by 100, that is 1/5 metal Y. So x2 quintals of scrap from B contain 1 by 5 x2 quintals. So total amount of metal Y present in the scrap is sum of these two values, 1 by 10 x1 plus 1 by 5 x2. So this is based on decision variables. This is the amount of metal Y present in the scrap. But the scrap must contain not more than 35 quintals. So what is the relation between this 35 and this amount? So not more than means less than or equal. So 1 by 10 x1 plus 1 by 5 x2 less than or equal to 35. So simplify this, both sides multiply with 10, we get x1 plus, if here we multiply with the 10, that means 2x2 less than or equal to 350. This is the third constraint corresponding to metal Y. Okay. So and next non-negativity restrictions. Since x1 and x2 are number of quintals, clearly they are greater than or equal to 0. Okay. So now graphical method. So what is the complete LPP problem? Objective function minimum z equal to 200x1 plus 400x2 subject to these three constraints and non-negativity restrictions. So here observe, the constraints are mixed type. Two constraints are greater than or equal type and one constraint is less than or equal type. Now apply graphical method. So in graphical method we represent inequalities on xy plane. For that we consider inequalities as equalities. Consider first inequality as equality x1 plus x2 equal to 200. So find intercept points on coordinate axis. First take x1 0, here substitute x1 0, x2 equal to 200, and next substitute x2 0, then x1 equal to 200. So these are the intercept points on coordinate axis for this line. Similarly, consider second line, x1 plus 3x2 equal to 400. Find the intercept points. Take x1 0, then x2 equal to 400 by 3. Next take x2 0, then x1 equal to 400. Next consider third line, x1 plus 2x2 equal to 350. Find the intercept points. Take x1 0, then x2 equal to 350 by 2, 175. And take x2 0, then x1 equal to 350. So these are the intercept points for the third line. Now draw these three lines on xy plane. Okay, right? So take the x-axis. So observe, so there is no negative range. So in the intercept forms, all are positive intercepts. So you need not consider negative part of x-axis and y-axis. Just consider positive quadrant. So this is y-axis, this is x-axis. So observe the range of limits. On x-axis, maximum range is 400. On y-axis, maximum range is 200. Okay, so we take on x-axis 1 centimeter equal 50 units. On y-axis 1 centimeter equal 20 units. Or you can take your own scale. Okay, so first point is to draw first line. To draw first line, first point is 0, 200. So 0, 200 is on y-axis. This is the point 0, 200. Second point is 200, 0. This is on x-axis. This is the point. Join these 2 points with scale and pencil. Okay. Now identify the inequality region. So apply substitute the origin in the inequality. So 0 plus 0, 0. Is 0 greater than or equal to 200? So it is not. So origin not satisfying the inequality. So inequality lies away from the origin. Okay. So away from the origin means this region. So this is the region for first inequality. Okay. Similarly, draw the next line. What is the next line? 0, 400 by 3, 400, 0. So 0, 400 by 3 means this is. This is 0, 400 by 3. Second point is 400, 0. This is. So join these 2 points. Now apply the inequality. In the second inequality, substitute origin 0 plus 0. Is 0 greater than 400? So no. So here also the region is away from the origin. Here also the region is away from the origin. Okay, right. So this is the region. This is the region. Okay, right. Third equation. First point 0, 175 on y-axis, 350, 0. Okay, so 0, 175 this point, 350, 0 this point. So join these 2 lines. Okay, now apply the inequality. Substitute origin in the third equation, third inequality. So 0 plus 0. So substitute origin in the third inequality, 0 plus 0, clearly 0 less than 350. So it is satisfying. Okay. So for third line, the region is towards origin, this side. This side. Okay. So now identify the common region for the three regions. For first two lines, the region is this side. For third line, the region is this side. So common region is, this is the common region. So this is the common region. This is the common region. Okay, right. So this is feasible solution region. Now identify the extreme points. So extreme point means it is intersection of two lines. Okay, so in this region, this is one extreme point, this is another extreme point, this is another extreme point. Okay, so let this point be A, B, C. Okay, so the feasible solution region is A, B, C, and the extreme points are A, B, C. Okay, right. So we have to find these coordinates of these extreme points. First, observe this A. This A is intersection of second line and first line. A is intersection of second line and first line. Equation 1 and equation 2. So solve those two equations. Subtract the second equation from first equation. So x1 gets cancelled. You get minus 2x2 equal minus 200, x2 equal 100. Substitute in 1. You get x1 equal 100. Next, B. So B is intersection of third line and second line. That means B is intersection of equation 2 and equation 3. So solve 2 and 3. Again subtract 3 from 2. You get x2. Substitute x2 in equation 2. You get x1. So B is x1 250 comma x2 50. Next, C. C is intersection of this line, that is 1 and 3. So C is intersection of equation 1 and equation 3. So subtract 3 from 1, you get x2 150. Substitute this in first equation, you get x1 50. So the extreme point C is x1 50, x2 150. So these are the extreme points. Now calculate the objective function value at extreme points. So A is 100 100, B is 250 50, C is 50 150. So substitute these extreme points in objective function value. Okay, first substitute A here. 200 into 100 plus 400 into 100, that is 60,000. Substitute second point. 200 into 250 plus 400 into 50, 70,000. Substitute C. 200 into 50 plus 150 into 400, this is 70,000. Since the objective function is minimization, we have to consider the smallest value. Okay, so the optimal solution exists at the extreme point A. So optimal solution occur at the extreme point A. So number of quintals of scrap from A is x1. x1 equal 100. x1 means the number of quintals of scrap purchased from supplier A. x2 is 100. That means number of quintals of scrap from B is x2 is 0. And minimum cost is 60,000 rupees. So this is the optimal solution to that problem. Okay. Now consider the another example. Solve the following LPP by graphical method. Max z equal minus x1 plus 2x2 subject to two constraints, x1 minus x2 less than or equal to minus 1, minus x1 plus 2x2 less than or equal to 4, and x1 x2 greater than or equal to 0. Okay, right. First we represent the constraints on the graph. So consider the first inequality as equality, x1 minus x2 equal to minus 1. Find the intercept points on coordinate axis. So first take x1 0, substitute here, minus x2 equal to minus 1, so x2 equal to 1. Now take x2 0, substitute here, x1 is minus 1. Next consider the second inequality as equality, minus x1 plus 2x2 equal to 4. Find intercept points, x1 0, substitute here, 2x2 equal to 4, x2 equal to 2. Next substitute x2 0, so minus x1 is 4, x1 is minus 4. These are the intercept points. So here observe, in the coordinate system there are negative values. So we have to consider negative axis also here. So for x1 there are negative numbers, we have to you have to consider the negative x-axis also. Okay, so draw these lines, take x-axis, draw y-axis. So use scale and pencil to draw the graph to get accuracy. Okay, so this is y-axis. Next, point the units. This is origin. This is origin 0. Take negative axis, since negative values are involved in the range. This is -1. Take 1 centimeter equal to 1 unit. This is -2. Take 1 centimeter equal to 1 unit. So this is -3. This is -4 on y-axis. This is 1. This is 2. Okay. So these points are enough to represent these two lines. Okay. Right. First, to draw the first line. So x1 0, x2 1. So x1 0, x2 1. This is the point. So 0 comma 1. This is the point. Next, second point. x1 minus 1, x2 0. x1 minus 1, x2 0. This is the point. -1 0. So join these 2 points with scale. Join these 2 points. So this is the equation 1. Now now find the inequality region. So substitute origin in the inequality. So 0 minus 0. Is 0 less than or equal to -1? So no. Okay. So that means origin is not satisfying the inequality. So the region lies away from the origin. That means this side. That means this side. The region lies away from the origin. Okay. So this is the first inequality region. Okay. Similarly, draw the second line. So first point is 0 comma 2. That is x1 0, x2 2, x1 0, x2 2. So this point. Second point, x1 minus 4, x2 0, x1 minus 4, x2 0, this point. So draw these 2 points with the scale. So this is the second line. Okay. Now verify the origin. So substitute origin in the inequality. 0 plus 0, clearly 0 less than or equal to 4. So for this line, the region is towards her. That means this side. This side. So this is the region for second line. Okay. Right. Now identify the common region. So for this line, this is the region. For this line, this is the region. So common region is this part. This is common region. Since x1, x2 are greater than or equal to 0, we have to consider the region in first quadrant only. Okay. So this is feasible solution region. This is feasible solution region. Okay, A. Now identify the extreme points. So extreme points are A. This is extreme point. This is another extreme point B. This is another extreme point C. So these are the extreme points. Okay. So the feasible solution region is ABC, which is bounded. Extreme points are ABC. Observe the region. We can easily identify the point A and B. A is 0 comma 1, B is 0 comma 2, C is intersection of 1 and 2. C is intersection of 1 and 2. So solve the equations 1 and 2. So add the two equations, x1 gets cancelled, we get x2 3. Substitute x2 in 1, we get x1 equal to 2. So C is 2 comma 3. From the graph B is 0 comma 2. From the graph A equal to 0 comma 1. Next, evaluate the objective function values at these extreme points. Substitute first point x1 0, x2 1. So that is 0 plus 2 2. Substitute second point x1 0 plus 2 into 2 4. Substitute third point minus 2 plus 2 into 3 6. That is 4. Okay. So since the objective function is maximization, we have to consider the largest value. So we have two largest values 4 4. So the largest value occur at two extreme points B and C. Okay, so in this case we get multiple optimal solutions. So optimal solution occur at the extreme points B and C. Since the objective function value at the extreme points B and C is 4, which is largest. Okay, so the optimal solution occur at two extreme points. The problem has multiple optimal solutions. First solution is B, that is x1 0, x2 2. Second optimal solution is C, that is x1 2, x2 3. And maximum of objective function value is 4. So max z equal 4. So this is the problem having more than one optimal solution, that is multiple optimal solution.